So what we're going to do is take our calculus approach to this. We're going to start by making an estimate of the area under the graph using shapes whose area we do know. And we're going to start with one of in the catalog we just mentioned, start with rectangles. All right, suppose we're trying to find the area underneath the graph here on the interval from x equals 1, so there we go, up to x equals 4. So we're trying to find the area shaded in here. The exact area is called, we're going to call that A square units. All right. Now, if we're going about that, how could we start? Well, we could start by drawing a rectangle that completely contains the area, or one that is completely contained by the area. Let me show you what those might look like. We're definitely have on this interval 1 to 4. One of the rectangles we could draw is that little rectangle there. Another rectangle that we could draw would be up at the highest point, down, across, and down like so. So, what does that tell us? Well, this area here in blue, which is about, well, which is 3 square units, that's less than the area in A, for sure. Because I can see the area in A graph is always higher than that, so to definitely have more area in A. However, I also have an upper limit here, and that's about 4.5 times 3. So this area, 4.5 times 3 would be 13.5. That area there, square units. Okay. So we don't know what A is, but we know that it's bigger than 3 and less than 13.5. For those of a different generation, it's smaller than an elephant, bigger than a bread box. That's not really that helpful, but it gives us an idea that we can at least somehow approximate the continuous area, the nonlinear area we're trying to enclose here. What else can we do to improve this? Well, we can think about using smaller rectangles to improve our estimate. Let's divide that into 3 intervals, each of width 1, and use different sized intervals. All right, what I'm going to do then here is break this into a blue, a red, and a green rectangle here. And what I'll do is go up on the left side of each interval and make a rectangle like so. The red one will start at the left and go up to the graph like so. And green, same thing. There we go. And we'll highlight it so we can sort of see the areas a bit more clearly. Now, notice what we're missing here. Those regions shaded in black that I just added, those are missing. But those little areas that are missing are certainly much smaller than the areas that were missing in the earlier slide when we used a huge rectangle over the entire interval. So if we take a look at this, what we can say is certainly area A is bigger than the sum of these things, but the blue area plus the red area plus the green area, all of that is going to be smaller than A. But now we've got an area of 1 and of 3. Let's do that out. 1 and 3 and 4. So that's less than A, or overall 8 is less than A, 8 square units. Okay, well that's a much better, much more limiting lower bound on the area that we're considering here. So that's great. And I think we can see that this approach might get us a fair ways into improving our estimates. In particular, we can generalize this by using any number of rectangles, and we expect that the estimate of the area will get better with the more rectangles we use. The narrower they get, the less missing area there's going to be. Now let's formalize this a little bit. That sum that we just generated on the graph was called the left-hand sum, because on each interval that we considered, we went up, there was a graph above this, let's say it looks like that, and we went over to the left endpoint and used that the height of the graph at that point as if the graph was actually constant. We sort of pretended, well, the graph's mostly close to that value on the entire interval. And there's no reason we had to pick that point. We could have picked any other point, and we'll see some other options of that later on. But to formalize this, we would have a few ingredients. We would have an interval from x equals a to x equals b. So if we divided this long interval into multiple small intervals, and the entire interval is from a to b, and we had n rectangles, or n intervals, then each of these rectangles would have a width of delta x, and the length of that is the total x interval divided by the number of subintervals. That's how we can get the individual width of each size. So this is just taking a long thing and dividing it into n pieces. So with that in mind, we can get a formula for how we would calculate that left-hand sum, or that area approximation, without having to draw it. So the left estimate using n intervals, the way we're going to define our values here is the initial value would be x naught, the last value would be xn. I just be a little bit careful here. N intervals, anyone who's done any programming, this is familiar. You have n intervals, that means you have n plus 1 boundary points. Just a quick sketch of that, just to make sure everyone's clear. If I divide an interval into 4 even intervals, 1, 2, 3, 4 intervals, I'm going to have 1 point, 2 points, 3 points, 4 points, 5 points that define the boundaries between those intervals, because there's always 1 left over at the end to define the final boundary, or there's 2 on the first interval, whichever way you like to think about it. In general, we would go up to n here starting at 0. That'll give us n plus 1 points. And we would just fill these in as necessary. And what we have here is a height. How would we get the picture of what we had before? We'd have the function going over top, and we would pick on this interval. Let's go to the left-hand endpoint and then go up to the graph there and draw a rectangle with height being the function at x naught, and the width of the rectangle being given by delta x, the width of each interval. They're all the same size. Then on the next interval, we'd go on the left-hand point of this entire interval here, go up to the left side, and then go up to the graph. That would be another height here. And then we'd have another width. And we do that until we got to the last interval. And on the last interval, of course, the point that we take is the left-hand endpoint, which would be xn minus 1 rather, the last point before the boundary at the end, and that would be how we do our sum. Notice we can write this in summation notation. It's not going to be a big feature of this course, but it's worth seeing if you have it, if you haven't seen it before. This kind of sum, you're letting I equal 1, and then you'd have f of x 1 minus 1 times delta x, and then I would equal 2. You would add f of x 2 minus 1 delta x, and that is fx1 minus 1 is fx0. fx2 minus 1 is fx1. So this is another way to compactly write out the sum that we have here. Again, not something that's terrifically important in this course, but it's worth seeing, and we will occasionally use this kind of notation for brevity. So if you can get used to that now. If you haven't seen it, please let me know in the forums. All right. One of the things we can do to generalize this again is not limit ourselves to on each interval looking at the left-hand endpoint. So on each interval up till now we would have gone up to the graph on the left. Of course we can also go up on the right-hand side, and let's say our curve is up here. On each interval we can go up on the right-hand side and build a rectangle out of that. And the formulation is almost identical. The only difference here is that we use, xi minus 1 in the left-hand sum. The right-hand sum is basically the same thing, except on each interval we'd take the right-hand endpoint and we'd start then at x1. Just doing a quick sketch again. On the first interval, we would pick our interval based on the value at the right-hand endpoint, and even on the last interval, we do the same thing, which would be the height at the last point, xn. So these are formulas you'll get some practice with in your assignments. And just to get some practice here, we're going to use 6 intervals. And that would mean on the interval from 1 to 4 here, that each of our intervals will be 0.5 wide. And we're going to do it with the left-hand rule, a left-hand sum, and we'll do it with the right sum as well, right-hand sum. Let's see what that looks like. So on the left sum, we would, on each interval, go up on the left-hand side. Let's try to make this as accurate as possible. And there we go. So the left sum with 6 subintervals here over the interval from 1 to 4 would be basically a height of 1 times a half, plus a height of 2 times a half width, plus a height of 3 times a half, plus a height of, looks like 3.5 times a half, plus a height of 4 times a half, plus a height of, there it gets a bit dodgy, let's say 4.25 times a half. So all of these terms are heights and widths, heights and widths for each one of these rectangles. And if we calculate the sum there, the nice thing about this is we can actually factor out the half. All the delta x's are all the same widths, so they're a common factor. And if we break those out, we'll have 6, 9, 13, 14, 18.25. And so that would, when divided by 2, would be 9.125 square units. Just double check, 6, 10, 14, 17, 18, yeah, 18.25. All right, so that is one way to get a sum that approximates the area. And notice this is a lower bound on the real area that's still closer than anything we've seen before. The lowest estimate we had before was 8, and now we know that the real area underneath this curve is at least 9 and 1/8. If we do the same thing, but using right-hand endpoints, for some reason this the right-hand endpoints seem less intuitive to most students, just to warn you. There's nothing fundamentally different about them. It's just that, yeah, they seem less intuitive. On each interval, I think because we like starting at the left. That's where we naturally go with our writing system. But on each interval, we're going to pick the right-hand endpoint, go up to the graph, and then go back left to build our rectangle. Like so, like so. On this interval, we go up on the right-hand side and back left to complete the rectangle, and like that. The nice thing is that we're actually reusing a lot of points here, just using them on different intervals. This first height here, I think we actually said it was, I should have drawn it more closely to the other one. More like 2 there. Let's see if I can erase here. Oops. My eraser is misbehaving here. There we go. There we go. And whoops. There we go. So we've got our height there of 2 and a width of a half. The next one has a height of 3 and a width of a half. The next one has a height of 3.5, width of a half. And 3 more to go. Height of 4, width of a half, height of 4.25, width of a half. That's this one here. And the last one looks like 4.5 or 4.5 and width of a half. Oops. There we go. And so again, we can bring the half factor out front of everything, and we'd have 2 plus 3 plus 3 is 2, 3, and 3 is 8, 12, 16, 20, 21 and 3/4. And we multiply that by a half, we'll get 10.5, 10.875, I believe. That's what we're going to get there. 3/8. Yeah, 7/8. So that gives us an upper estimate. Now look at how close these two estimates are to each other. These two estimates are almost, they were certainly within about 1.5 units of each other. So even with these crude rectangles, we've got a pretty good idea about the size of the area that we're trying to calculate underneath the actual curved shape of the graph. And it's bounded between 9 square units and 10.8 square units. So we're well away into having a strategy that looks like it's going to work to find the areas underneath curved surfaces. A couple of quick general properties. When will the left approximation of the area be greater than the right? Well, we just saw an example of that. Whenever the function's going up, if we pick an interval and we use the left-hand endpoint, then we're going to get a short rectangle there. But if we use the right-hand endpoint, we're going to get a taller rectangle. So whenever f of x is increasing, or you could get into derivatives as well. We won't bring that in for now to complicate things. But simply if the function is increasing, when will the left be greater than the right? Opposite case. Left will be less than the right in that case that we just saw there. My apologies. And so the opposite would be true if the function was decreasing. Then the left-hand endpoint would give us a rectangle that's nice and tall because the left-hand point is higher up than the right-hand endpoint, like so. So if f of x is decreasing, then the left-hand sum will be larger than the right-hand sum. When will left n be an overestimate for the area? Well, actually, there's our picture again. When f of x is decreasing. If on each interval the function is going down, but we use an area based on the uppermost point, the leftmost point, if the function is going down, our area rectangle is going to be larger than the area underneath the curve. And so whenever f of x is decreasing, we're going to get an overestimate using the left-hand sum. And likewise, when f of x is increasing, we're guaranteed again that the left sum on some interval, we go to the left-hand edge, is going to be much smaller than the actual area underneath the, not much smaller, certainly smaller than the area underneath the curve. And I think that makes a good introduction to the idea of calculating areas underneath curves. We'll explore this more as we move forward.